Hi everyone, my name is Asaf Rosin, and I will talk about testing subsequence freeness. This is joint work with Rosin. For sequences T and W, T is said to be W-free if it does not contain W as a subsequence. For example, this sequence does contain the sequence 1, 2, 3, 4 as a subsequence. And our task is to decide whether a given sequence T is W-free or is epsilon far from being W-free. And we focus on three main things. First, we focus on sample-based testing. We are not allowed to use queries, only samples. Second, we focus on the distribution-free model, in which samples are chosen according to an arbitrary probability distribution. And third, we focus on one-sided error testing. So we must accept if T is W-free. We note that the distance from W-freeness is measured with respect to P. That is, the pair TP is epsilon far from being W-free if the minimum weight of symbols that should be modified in order to make T W-free is bigger than epsilon. We also note that most previous property testing results are with queries and not samples, and among the works with samples, most of them are using uniform samples and not arbitrary samples like in the distribution-free model. During this talk, N denotes the length of T, and we'll often call T a text, and K denotes the length of W, which we'll often call a word. Since we focus on one-sided error testers, our question is actually the following. What is the minimal number of samples such that for every word W of length K and every pair TP that is epsilon far from being W-free, a sample of size S from T contains W as a subsequence with probability at least 2/3. The number of sample S may depend on parameters like K and epsilon, and the samples are chosen according to P. About previous work, Freitag et al. Showed that K squared log K over epsilon samples suffice for testing its subsequence freeness under the uniform distribution in the one-sided error testing model. And this raises some natural questions. First, can we do better? And second, can we generalize to other distributions? And I'll try to answer these questions during this talk. Our first result is that the sample complexity of one-sided error sample-based testing of subsequence freeness is K over epsilon under the uniform distribution. This means that, yes, we can do better. Moreover, this upper bound is tight. And more interestingly, the lower bound of K over epsilon holds for testing W freeness for every subsequence W, and not only for some worst case choice of W. Regarding the second question, we prove our result of K over epsilon as an upper bound holds even in the distribution-free model, and not only in the uniform samples model. Another natural question is, can we do better with queries instead of samples? And the answer is no, at least for the one-sided testing model. Canon et al. Showed a lower bound of K over epsilon queries for one-sided tester of K monotonicity of Boolean functions over the line. And as this is a special case of our problem, we get that this lower bound holds in our case as well. About related results, Balkan et al. Showed that an upper bound of square root of K times poly 1 over epsilon uniform samples for testing K interval functions over 0, 1. This is with two-sided error. And several other related properties were studied using queries, like K monotonicity, forbidden order patterns, and many more. You can see our papers for much more detailed related results section. To gain some intuition about our results, we begin with a simple example. So let W be a word that does not contain repetitions. So without loss of generality, we can assume that W is 1 up to K. And let T be just epsilon n plus K repetitions of W, and the rest filled with zeros. So as T contains more than epsilon n disjoint copies of W, it can be easily seen that T is epsilon far from being W-free. This holds because in order to make T W-free, one must modify at least one symbol from every disjoint copies of W in T. And we want to analyze this example and answer the following questions. How many samples are sufficient to obtain evidence of W? I will give the analysis idea here. So first, we use the personalization technique. It allows us to break dependencies between probabilistic events, and it simplifies the analysis. So we can assume that each symbol is independently sampled with probability rho, which is about S over n. Now, we define a probabilistic procedure. It traverses T while selecting samples on the fly. And it maintains a counter for the length of the prefix of W already sampled. We expect each copy of W to increment the counter with probability rho. This is because if you already sampled 1, 2, and 3, and we now seek the symbol 4, we know that in each copy of W, the symbol 4 exists. So each of these copies of W will increment our counter and expand the prefix of W we've already sampled with probability rho. We expect the counter to reach K after about K over rho copies. And when the counter reaches K, we know that we have sampled the entire word W, because W is of length K. Since we have more than epsilon n copies, this means that K over epsilon samples are sufficient here. Going to the general case, we have 3 issues. First, T might not have such a convenient structure as in this simple example. The second issue is that W may contain repetitions and not be just 1, 2, 3 up to K. And the third issue is that the underlying distribution may not be the uniform distribution. To address the first issue, we present a combinatorial characterization. We assume that W may have repetitions, so without loss of generality, W equals to 1, 2, up to K. And notice that as the example, the simple example, suggests, disjoint copies of W in T are important for the analysis. In fact, it was already observed that if a text T is epsilon far from being W free, then there exists more than epsilon n over K disjoint copies of W in T. This is true because if T has less than epsilon n over K disjoint copies of W in it, then all the symbols that participate in these copies are less than epsilon n symbols, and one could modify them all and make T W free, which is a contradiction to the assumption that T is epsilon far from being W free. So a natural question following this is whether we can prove better. And the answer is yes, we can. We show the following lemma. If T is epsilon far from being W free, then there exists more than epsilon n disjoint copies of W, not only epsilon n over K disjoint copies. And building on this lemma, an adaptation of the previous probabilistic argument for the simple example can be used to show the upper bound for every text T which is epsilon far from being W free. We now address the second issue, that W may have repetitions. So here in this case, the same observation holds. If a text T is W free, then the same argument showed that there exist at least or even more than epsilon n over K disjoint copies of W in it. And one might ask whether we can prove better this time in the general case as well. But the answer is no. As the following straightforward example suggests, there is a text T which is epsilon far from being W free, this T and this W, but T contains no more than epsilon n over K plus 1 disjoint copies of W. So we cannot prove better than this observation suggests. And this implies that we need a more refined notion than disjoint copies. And our suggestion of the refined notion is the following. We define all disjoint copies to be copies that may overlap, but not on the same role in W. For example, this text contains a first copy of W and a second copy of W, but these copies are not disjoint. They are all disjoint because their shared symbol, this one, is the second symbol of W in the first copy, and the first symbol of W in the second copy. The advantages of this definition is that it is weak enough so that every epsilon far text contains more than epsilon n such copies of W, but it is strong enough to facilitate an adaptation of the probabilistic argument from the simple example and generalize this to any W and T. We generalize this to the following statement. For every text T and word W, the distance of T from being W free equals the maximum number of all disjoint copies of W in T. Due to lack of time, I will not describe the details of the proof for this lemma, this combinatorial characterization, but I will say a few words about the high-level proof idea. So we built a flow network called NTW such that, first, the maximum flow in the network equals to the maximum number of all disjoint copies of W in T. And second, the minimum capacity of a cut in the network is at least the distance of T from being W free. Just to give you a feeling, here is the constructions of NTW for the example in the previous slide. To sum things up, we have already analyzed the simple example. We show how to handle the case of general text T and the case of general words W that may have repetitions. So we have achieved our first result. The sample complexity of one-sided error sample-based testing of subsequence freeness under the uniform distribution is K over epsilon. We now address the final issue. We show a sample complexity preserving reduction from the distribution-free case to the uniform distribution case. Again, I will not say the details of this reduction, but only provide an outline. So our reduction consists of two parts. In the first part, we reduce distribution-free testing of general words to distribution-free testing of words in WC, which is a specific set of words. It is the set of all words that does not contain consecutive equal characters. For example, 1212 lies in this family WC, but 15523 does not because of the consecutive equal symbols here. In the second part of our reduction, we reduce distribution-free testing of words in WC to testing under the uniform distribution, which we have already handled in Theorem 1. Let's sum what we have done so far. We have analyzed the simple example. We have handled the case where T does not have a convenient structure, and also the case where W is general and may contain repetitions. And then we have handled the case where the distribution is not uniform, but a general distribution. So in conclusion, we have proved the following theorem. The sample complexity of one-sided error distribution-free sample-based testing of subsequence freeness is K over epsilon. Turning to the lower bound, we can observe that the simple example where W is just 1 up to K and T contains many consecutive repeating copies of W and the rest zeros actually gives the lower bound of K over epsilon. The analysis here is similar to the upper bound analysis for this example, but it is slightly more complicated. As in this case, we are not allowed to miss any copies of W, and we have some edge cases that needs to be handled carefully. An interesting question is whether there exists words W for which the sample complexity is smaller than K over epsilon. Interestingly, for every word W, we show a related construction. This time, the text does not contain repetitions of the entire W, but only repetitions of the distinct symbols of W. And this construction shows the necessity of K over epsilon samples for every W. Thank you very much for listening to my talk. And if you have any questions, you are welcome to contact me by email or to attend my WOLA live presentation. Thank you.